Hello everyone, welcome back to our second session. In this session, what we're going to be doing is looking at a totally new, in some ways, but in some ways familiar build upon what we've been covering so far. So what we're going to look at today is integer programming. We're going to do it in a couple different ways. The first way we're going to do it is by looking at the first of three possible integer problems. The first problem is very, very similar to everything we've been doing. But the key difference is that all our answers must be proper integers. Integer just means a round number. 3 is okay, 3.23 is not okay. 3.29, 3.8, not okay. 4 is okay. It must be a full round number or an integer. Now, we've seen time and time again kind of answers that, while mathematically correct, are actually impossible. We had situations where you can order 4.28 television commercials. That makes no sense at all. How is 0.28 of a television commercial? We also saw a situation where you could order, you were eating 4.23 potatoes. What kind of person has the time to divide into 4.23 potatoes? It's almost impossible. So what we have is, with integer programming at the base level, with the total integer model, which is what we see here. The first of our models is the total integer model. This is very, very similar to what we've been doing. It's essentially the same as what we've been doing. The major difference, however, is that in this case, all of our decision variables, all decisions must be full integers. We can no longer have point anything. Let's look at a very basic example. The owner of a machine shop is planning to expand by purchasing new machines, presses, and lathes. This wild background information is relatively unimportant, so let's leave it clear for now. Going to the next section. The owner has estimated that each press will increase profit by $100 per day. That's key information. Each lathe will increase profit by $150 daily. Again, key information. The number of the machines the owner can purchase is limited by the cost of the machines and the available floor space. So now we have two constraints. That's what we've learned here. This should be very easy for you right now. This is a very basic question, and the key reason we're covering it is to introduce a new concept as simply as possible. However, even if it wasn't simple, it's quite easy. All we're doing is we're modifying in a very, very, very small way everything we have learned so far. So, let's have a look. Continuing on, the requirements for floor space and purchasing prices are listed below. Press, 15 feet of floor space, $8,000. Lathe, 30 feet of floor space, $4,000. Some more key information here. The owner has a budget of $40,000 for purchasing machines. And 200 square feet available of floor space. The owner wants to know how many of each type of machine to purchase to maximize the daily increase in profit. So now we know we want to maximize the daily increase in profit. So we make this bold. We've covered all the key information here. So as we always do, the first thing we're going to do is our objective function. We've been working with some complex objective functions recently. Here we're going to take it all the way back. This is almost what we studied in the first week of classes. So max z is equal to 100. We see here each press is $100, so 100 x1 plus each lathe will increase profits by 150 daily. 150 x2. And again, this is intensely simple because we want to go through this as easily as possible for now. So we go down here, C1, and we see that price is 8,000 and 4,000, and we have 40,000 available. So our price will be 8,000 x1 plus 4,000 x2. And it has to be less than or equal to $40,000. Now, in that situation, all we've done is taken the information and rearranged it into our known constraint format. This should be intensely simple now. Moving on, C2. And here we have 15 x1, because we know 15 feet of square space for a press, plus 30 x2, 30 feet of floor space for a lathe, must be less than or equal to, very simply, 200 square feet. Now we see right away, and I'm going to show you this quickly just for explanation's purpose. Here we have 15 and 30 must be less than or equal to 200. So we know right away we're not going to get an even number. So how do we solve a problem like this? Let's check. Let's go to QM right now. Now the key difference here, and I'm going to show you right now, is that we have to, when we click on module, we've always checked linear programming prior to this. However, we're not doing strict linear programming anymore. Instead, we're doing integer and mixed integer programming. We're doing a different situation where we're doing integer and mixed integer programming. So we click on this. We open a new file. And here we go. So let's call this the press and lathe total integer example. Now we saw from over here we see over here that we have two decision variables. Let's open a new one just to go step by step. So one more time, we'll call it press and lathe total integer Number of constraints, we know very simply, number of constraints is 2. We see that right here. Number of variables is 2, and it's a maximization. As I said, we're going right back to the basics because what we want to do is we want to focus on learning the new concept as easily as possible. So we click OK. Let's label our columns. X1 in this situation, press. X2, lathe. Constraint 1, floor space. Constraint 2, press. Now, we've got a couple new things here, but that's not important for right now. What we want to do is we're going to maximize presses 100. Lathe 150. Floor space for a press 15 feet. For a lathe 30 feet. And we have a total of 200 feet available. So it must be less than or equal to the 200 feet available. Our price is $8,000 for a press, $4,000 for a lathe, and we have less than or equal to $40,000. So all we've done is we've entered the base information that we found right here. So what do? Same thing we've always done. We're going to hit solve. The key here, it's showing right now. We want integer, real, or 0, 1. Integer, real, or 0, 1. This is something that we have to consider because now we're telling the computer what kind of variable we'll be looking at in this situation. So we want an integer number. Over here again, we want an integer. Real is fractional. 0 to 1 we'll look at later, but for right now we want integer numbers. That's only important if you're doing a mixed problem that we'll talk about later. So we hit solve. And what we see here is that we should buy 1 press and 1 lathe. That's important to remember. 1 press and 1 lathe. I'll write that down here just for right now. 1 press, 6. We'll do it over here. 6 lathe. Now that seems pretty interesting. We have a solution value of 100. Let's edit the data because we want to go back. If we buy 1 press, we see right here that's 15 feet of floor space. If we buy 6 lathe, that's 180 feet of floor space. 180 plus 15 means we have 190 feet of floor space is being used. 195 feet. We have 200 available. We're not using all of the floor space. That seems to me like we're wasting floor space. But the key here is because we're doing integers, because we're focused on integers, what we're seeing is that if it gives you an unrealistic number like 1.5 lathes, that's automatically canceled out. The computer realizes we're wasting something, but it knows you cannot buy a fraction of a lathe. You cannot buy a fraction of a press. So that means we will never be able to use all of our floor space. The computer's gotten us as close as possible to that situation. So the integer solving, all it does is it solves basic problems that we've looked at, total integer, and it also allows us to choose real options. I can hire 3 people. I can't hire 2.7 people. So it gives us real choices, and this brings us a little closer once again to real life applications of linear programming. Hopefully everybody's clear on this. I'm going to end this section, and we'll come back with section 2 in a moment. Thank you for listening. Thank you again. Bye-bye. Hello everyone, welcome back. In this section, we're going to look at our second type of integer problem. This is a 0-1 integer model example. The difference here is our decision variable, our choice now, can only be 0 or 1. Nothing else is possible. 1 if we choose to do it, 0 if we choose not to. What we're doing is we're making a choice. Choose this or do not choose this. For example, if I say you can choose candy bar, chocolate chip cookie, or ice cream. If you choose 1, 0, 1, you're choosing candy bar and chocolate chip ice cream. And ice cream, not chocolate chip cookie. So it's a little confusing now, but hopefully when we look at it together, it becomes a little more clear. So let's as always, let's begin with reviewing our question. Let's get the key information. A community council must decide which recreation facilities to construct in its community. So right now we know that we're choosing what to construct. We do it or we don't. We build it or we don't. So 4 new recreation facilities have been proposed: a swimming pool, a tennis center, an athletic field, and a gymnasium. We're choosing to do these or not. So in that situation, very simply, we're choosing to build it or not. These are our decision variables. So our variables are swimming pool, tennis center, athletic field, or gymnasium. These are our choices. These are the decision variables we will have to select between. So let's continue reading. The council wants to construct facilities that will maximize the expected daily usage. This is a key point too. We're trying to maximize our expected daily usage. They're subject to land and cost limitations. So here we see some of our constraints. The expected daily usage, I spelled this wrong. Expected daily usage and cost and land requirements for the facility are as follows. In this information here, it gives us our expected usage, the cost for each facility, and the land requirements. We'll see what we can make sense of with those later. The community has a $120,000 budget and 12 acres of land. Because the swimming pool and the tennis center must be built on the same land, however, only one of these two facilities can be built. This is a new type of constraint, something we haven't seen yet because we haven't worked with problems like this. There are several in 0-1 problems. There are several special situations. Because of that, we have to review all of them before I can expect you to do any homework questions. So the good news is, today, there are no homework questions. However, we do have to get through this example. So please be patient. This is a special example, as I said, a special constraint, and we will discuss it momentarily because it's not immediately clear, and it might not be until we look at it correctly. So we know our variables. First thing we do, as always, our objective function. So we're trying to maximize Z, or maximize our usage of the facilities we construct. To do that, right here, max Z usage is equal to 300 x1. And we get that from here. If we build a swimming pool, 300 people will use it, plus 90 x2. Right again, right here, 90 if we have a tennis center, plus 400 x3 plus 150 x4. So what we've done here is we've shown our usage statistics because our objective function is meant to maximize our usage statistics. And that's what we've indicated here. Once we have our objective function complete, we move to the next step, which, as always, is constraints. So C1 is budget, 120 up. So here we have 35,000 x1. If we build a swimming pool, it will cost $35,000 plus 10,000 x2. If we build a tennis court, it will cost $10,000 plus 25,000 x3 plus 90,000 x4. This is our budget. This is the budget that we have seen for each of these items, but we know we have a total budget of less than or equal to $120,000. Our first constraint is budgetary based. If we build a swimming pool, it costs $35,000. If we build a tennis court, it costs $10,000. If we build an athletic field, it costs $25,000. If we build a gymnasium, it costs $90,000. We can choose any combination of these, but it must be less than $120,000. C2. In this situation, for C2, we have a scenario where 4x1 and we see that here. If we build a swimming pool, it requires 4 acres of land. So 4x1 plus 2x2 plus 7x3 plus 3x4. All of these numbers represent how much land will be built if that item or how much land will be used if that facility is constructed. We have 12 acres available, so it must be less than or equal to 12 acres. That's our second constraint. So far, everything we've seen is relatively straightforward. Let's look at constraint number 3. In this situation, we have a third constraint. The swimming pool and tennis center must be built on the same land. So, only one of these can be built. This is called, and we'll put it over here for now, this is a contingency constraint, meaning only one or the other is possible. We indicate that like this. 1 x1 plus 1 x2 is less than or equal to 1. And I'll explain why now. If we choose to build a swimming pool, then this is 1. This cannot be 1. This must be 0. If we choose to build this one, the tennis center, the swimming, it is equal to 1. This must be 0. If we choose to build neither of them, it's less than or equal to 1. That's a valid choice. If we choose to build the swimming pool and the tennis court, this is more than equal to 1. That is not a valid choice. That is not possible. In the next class, I'm going to review contingency constraints. I'm also going to look at the other special situations we have with integer models. So please pay attention when I do introduce those, because they will come up time and time again whenever we do whenever we do 0-1 modeling examples. We will be using those again and again. Hopefully everybody's following along. Hopefully everybody is relatively unconfused. So right now, what we'll do is because we've established our constraints, it's a relatively straightforward thing to come up here, open a integer and mixed programming example, and open a new file. Let's call it our recreational facility example. How many constraints do we have? 1, 2, 3, 4. 1, 2, 3. How many decision variables? Constraints was 3. Decision variables, we have 1, 2, 3, 4. And we're trying to maximize usage. So we hit OK. Now, we're going to label everything appropriately because hopefully that will help us to understand. So the first one is swimming pool. The second, we'll make all of these a little bigger. We'll do that after. For now, let's see everything. So the second is tennis center. The third, athletic field. Fourth, gymnasium. So here, we have to ask ourselves, what are we trying to maximize? Because we are trying to maximize. We're trying to maximize, in this situation, usage of facilities. So we come over here to swimming, and we make this 300. Over here to tennis, we make it 90. The athletic center, 400, and the gymnasium, 150. This is what we are trying to maximize, the usage of these items. So now our first constraint, that's what we enter now, is our budget. And we know if we build a swimming pool, $35,000. If we build a tennis center, $10,000. If we build a gymnasium, $25,000. And if, oh, not gymnasium, athletic center. And if we build a gymnasium, $90,000. All total must be less than or equal to $120,000. That's our budget. And again, our results will be either 1, we build it, or 0, we don't. So if swimming pool is 1, that means we're serving 300 people, and it's going to cost us $35,000 to build. The second constraint, land requirements. We know it's 4 acres if we build a swimming pool, 2 acres if we build a tennis court, 7 acres if we build an athletic center, and 3 acres if we build a 3 acres if we build a tennis court. Less than or equal to the 12 acres we have available. Our final constraint, and this is swimming pool or tennis. And we see right down here, it's very easy to set up if we've put together our constraints properly. This should be relatively painless. So let's click over here. Swimming pool is 1. Tennis center is 1. And those two added together must be less than or equal to 1. Now, we've put together everything properly. There are no issues. But we have to adjust one thing. Down here, if we do integer, the computer will choose 1, 7, 9. If we choose real, the computer will choose 1.4, 7.2, 11.6. If we choose 0 to 1, the computer will choose only 0 or 1. 1 means we do build it. 0 means we don't. So we change each of these 4 to 0, 1. Okay, that is the major difference from what we've done in the past until now. So we're making each of these 0 and 1. Are there any questions? Hopefully not. So what we do, as before, we solve. Now this may look confusing initially, but let's talk about it for 1 second. We can close this now because we've dealt with this already, and we'll maximize over here. Swimming pool is 0 to 1. Those are our choices. 0, don't build. 1, build. The value is 1. So this tells us our correct choice is to build 1 swimming pool if we're trying to maximize usage. We also see the tennis center is 0 to 1, and the answer is 0, meaning don't build. Building a tennis center will not optimally serve our customers. An athletic field, 0 to 1 again, and the choice is 1. So in this situation, we do build the athletic field. If we go back and we look at the data, a swimming center does 300, an athletic center does 4. If we build those two, we're serving 700 people. That's what this shows us. A total of 700 people are being served if we build a gymnasium and if we build a tennis center. Let's look at the data again. If we build a gymnasium and a tennis center, we're spending $35,000 plus $25,000. So we're spending 70,000. That's less than 120. Why are we only spending 70,000? Number one, if we also build a gymnasium, we go over budget. And number two, we can only build a swimming pool or a tennis center. We built the swimming pool, tennis center is out. We built the swimming center and athletic center, gymnasium's too expensive, it's out. If we look at land, we're using 4 acres and 7 acres, a total of 11 acres. We only have 12 available. So again, by definition, tennis center, gymnasium are impossible. Finally, one or the other, and that's what we've shown here. It can only be a swimming pool or a tennis center. If it's both, it's above 1 and it's not a valid answer. So in this type of solution, what we've done is we've found optimal choices in terms of choosing or not choosing something. We will look at this more carefully next time. Again, I can't assign homework yet because you aren't aware of the full depth. So congratulations, there is no homework this weekend. And we cannot proceed any further because if I cover mixed or mixed problems, it will run well over our allotted time period. So good luck, everybody. I'm happy, hopefully all of you got the homework done by tomorrow. Have a wonderful weekend, and I'll see all of you next week. Thank you again. Have a great day.